Can you see that?
Looks good.
Okay, great, thanks. Okay, great. So first of all, thank you for the organisers for organising this very nice workshop. Very nice to be here. Yeah, so my name is Cameron, and today I will be talking to you about the interplay between EFTs in the form of the SMEFT and proton structure in the form of Parton distributions. And we'll be doing it in the context of high energy Drell-Yan data. And just a bit of advertisement before we begin. This project appeared on the archive just last week. So if you'd like to read more about it, then you can find it at that ID. Okay, so since this is an EFT workshop, and this project also includes important contributions from PDFs, I just want to give a bit of background about that. So PDFs describe the Partonic content of protons, and therefore they're a very important ingredient for LHC physics, because we collide protons at the LHC, obviously. And these PDFs depend on two variables, so on Bjorken X, which is a non-perturbative dependence, and also on the energy scale. And because of this non-perturbative dependence, we have to fit the X dependence. So what we do is we perform a global fit via this sort of master formula. So we have sigma, which is the experimental data, and the sigma hat, which are the corresponding Partonic cross-sections, which are computed in perturbation theory. And then using this, we're able to extract the PDF. So here, for example, when we collide two protons, we have F1 and F2, one PDF for each proton. And then we are able to extract the PDFs with some corresponding uncertainties. And importantly, PDFs are process independent. So you can fit them to some set of data and apply them to whatever process you like. But importantly, the more data you include in your fit, the higher the precision. So it's important to include a wide array of data in your fits. Okay, so now I come to the problem, which is we're addressing in this project, which is that when you perform a PDF fit, you have to assume some theory. So you have to assume the sigma hats. And of course, typically what's done is you assume the standard model. So this means that your PDFs are essentially standard model PDFs. So when you do your EFT analysis, you then have to take some PDFs. And of course, you then take standard model PDFs because that's all that's really available. So when you compute, say, a BSM cross-section, sigma BSM, you have an inconsistent calculation because only part of the ingredients are actually assume the new physics contributions. So in the context of the SMEFT, where we're looking for subtle deviations, we are interested in ascertaining how valid this assumption is. And this really leads to the question of, can the SMEFT be constrained correctly using standard model PDFs? And if not, how big a mistake is one making by assuming that standard model PDFs are safe to use? This was first studied in this paper here a couple of years ago, where they looked at DIS data in particular. And this made sense because DIS data really forms the bedrock of PDF determinations. So it was a very sensible starting point. And here we're going to extend this by looking at some more data. So as I mentioned earlier, the data that we're looking at here is Drell-Yan tails, or high mass Drell-Yan. And this is an interesting process to look at because it's important in both PDF determinations and also EFT determinations. So Drell-Yan data in general provides important constraints for PDFs in the for quarks and antiquarks, and say the QQ bar luminosity. But you could also expect that you could find distortions from new physics contributions in the tails of these Drell-Yan distributions, as you can see, for example, in the right-hand side. Okay, so now we have the process we're going to look at. We would like to pick some benchmark scenarios in which we can study the interplay between PDFs and the SMEFT. So in our paper, we look at two different models. So first of all, we have a flavor universal electroweak oblique corrections. So we have these two operators, these two Wilson coefficients W and Y, which I'll talk about more in a second. And then we also have a flavor-specific 4-fermion operator, which couples muon pairs to bottom quark pairs. And this was motivated by the anomalies in RK star, for example. I haven't got time to discuss both models in this talk, so I just focus on the first model in what follows. Okay, so these are the terms that are added to the Lagrangian. So we take this particular model and we map it to the SMEFT, and we find that there are 7 relevant SMEFT operators. These corrections, the so-called electroweak oblique corrections, basically parameterize modifications to the self-energy of the electroweak gauge bosons. So what they do is effectively modify the propagators of the electroweak gauge bosons. And in fact, if you want to try and look at this and map the operators to dimension 6 in the SMEFT, there are 4 such operators, S, T, W, and Y. But we only focus on W and Y here because, first of all, S and T are well constrained by precision LEP data, and also they have a weaker Q² dependence. So since we're interested in high energy data, we're safe in just focusing on W and Y here. Okay, now we have our process and the models. I want to talk a bit about the methodology that we're going to use to look at the interplay between PDFs and the SMEFT. So first of all, just to go over what you might typically do. So looking at the standard model PDF case. So what you would do to extract, say, some bounds, some constraints on your EFT parameters, is you take a set of data, make the predictions for these data, and you use a fixed PDF set. We then might compute a chi-squared for a set of Wilson coefficients. So here is the sort of typical chi-squared formula that you've seen in the previous talks, where we have D the data, T the theory, and the covariance matrix sandwiched between, which encapsulates the uncertainties on data and the correlations between them. And then given sort of sample of chi-squared values, you can fit a function to them, and then you can extract your bounds. And crucially, what's done here, as I mentioned earlier, is that when you compute your T, you assume standard model PDFs. Now what we do in this project, which was again first studied a couple of years ago, is you do the same procedure, but for each value of the Wilson coefficient that you take, you do a consistent PDF set. So if you scan, say, 10 values of the Wilson coefficients, you have to do 10 PDF sets. There are 10 PDF fits. And then when you compute each theoretical prediction for each particular Wilson coefficient, you then do a consistent, make a consistent theoretical prediction. So both the PDFs and the Partonic cross sections assume the same value of the Wilson coefficient. Okay, now a bit about the actual settings we use when we are doing these fits. So these are the PDF fits are all done with the NMPDF framework, and we start with a basis of just DIS and low mass or on-shell Drell-Yan data, which we take from the latest NMPDF release 3.1, and we exclude all other data. So, for example, JETS data, top data, so that we have, in a sense, a clean starting point. And then we on top of this, add the important for our study high mass Drell-Yan data. So in terms of current data, we add 5 data sets, all neutral current Drell-Yan sets from Atlas and CMS. And then later in my talk, I'll talk about some projections we make for future data. So there we look at the high luminosity LHC. Regarding the standard model theory, we use sort of state-of-the-art calculations. So we have next to next leading order QCD plus next leading order electroweak. And then for the SMEFT sector of the theory, we apply the SMEFT corrections by the K-factor approach. So we apply a bin by bin multiplicative factor that encapsulates the correction. For W and Y, we do just include the linear terms, but the other model we include also the quadratic. But here the linear term dominates, so we just include that. And we apply these corrections to both DIS and Drell-Yan data. And here's just an example of the corrections that we get for an example data set. So this is the CMS 8TV data set that goes into our fits. The blue shows the relative experimental uncertainty, and then the gold and green just show the SMEFT corrections. And as you can see, as you go to higher energies, the corrections get larger. So this is why this model is interesting in the context of high invariant mass Drell-Yan tails. Okay, so now I will start to actually answer the question I posed earlier, which is, can the SMEFT be constrained correctly using standard model PDFs? And here I look at just current data, and we're looking to see whether if you do a consistent treatment, do you find a different answer to what you would do typically using standard model PDFs. So here are some results from some 1D scans in W and Y. In each plot, so dashed blue is what you would typically do. So this is with standard model PDF sets, and then the orange instead is what you do when each value of the Wilson coefficient, you do a consistent treatment of the theoretical predictions. And what you can see is that in each case, the orange is slightly wider than the blue. And also for Y, you see a slight shift in the central value. We find that we get a sort of 10 to 15% broadening of the 95% confidence interval bounds. But when we include PDF uncertainties on the blue curves, so on the standard model PDF set results, this becomes a slight shrinking. So although we can see visually some effect, this effect is within PDF uncertainties. We can then also look at this in a complementary way by looking at some search data. So this search data is not suitable for inclusion in PDF fits. It's not measurement data. So we just take the PDF sets from the previous slides and apply them here. In particular, we look at an Atlas 13 TV Z prime search with the full run-to luminosity. So search data benefits from the fact that you have a higher luminosity typically than the measurement data, and also so because of this you have a higher reach in invariant mass, and also you have thinner binning, which helps in the EFT analysis. So again, I just show W here, but the picture is the same for Y. And what we find here is that the effect of PDF uncertainties is much smaller, and in both cases, so whether you include the uncertainties or not, you find a small broadening of the 95% bounds for W and Y. So to sort of summarize the state of affairs with the current data, in the unfolded data, we can see a visible effect, but it's within uncertainties. While with the search data, which is not included in the fits, we find a slight widening beyond the uncertainties. So the point here really is that with the current data, the effect is mild, but we are starting to see some impact. And so potentially in the future, when we have much more data from the high Lumi LHC, we might expect to see some more dramatic impacts. And that's what I'll look at now. So exactly the same thing, but with future data. Okay, so similarly to as Giacomo was talking about in the last talk, we make some high luminosity projections. And we're interested in seeing the effect in the most sort of extreme example we can find. So what we do is consider an optimistic scenario. So we're trying to calculate really the optimal reach that you could get with a high Lumi LHC in this context. To this end, we consider a center of mass energy of 14 TeV, an integrated luminosity of 6 inverse attobarns. So that's 3 inverse attobarns from each of Atlas and CMS. And we have this parameter f red cis of 0.2, which means that we take some 13 TeV reference measurements and we reduce the systematics by a factor of 0.2. We then generate the data by fluctuating the theory within some experimental uncertainties. And here, for example, you can see how this looks. So we have a data theory comparison for, in this case, it's the charge current muon channel data. And one point I want to highlight is that if you look at the bottom panel, you see the size in each bin of the statistical error versus the systematic error. And in the highest bins, we find that the points are statistics dominated. So we don't expect that our reduction factor of 0.2 whether we chose something different, we'd find particularly different results, because it's these bins that are these high stats bins that are the stats dominated bins that are most important for our analysis. So using this, we can repeat the procedure and look at the results. And here we do a 2D scan in both W and Y. And the blue, again, is the standard model result of the standard model PDF set, so the inconsistent treatment. And then in orange, we have the consistent treatment. And in each case, we plot the 68 and 95% confidence bounds. And what we see here is that we get a significant broadening, especially in W. And when we include PDF uncertainties, we still find that the broadening is very significant. And I suppose the main message really here is that in this case, if you're neglecting this interplay between PDFs and EFT, then you can get a significant underestimation of the uncertainty on your EFT parameters. Here I sort of summarize these results by showing two panels. So we have the W results and the Y results in all three scenarios that I've shown already. So we have three groups. We have the unfolded data on the left, then in the middle we have the search data, both current, and then on the right we have the High-Lumi projections. And I just want to highlight the case of W, which is, I suppose, the most stark example of what we're seeing here. So if you did the typical thing of just assuming standard model PDFs, so you just had the green results, then what you'd see is that, or what you'd conclude is that when you add the high luminosity data, your bounds become significantly tighter. And what we find when we do the consistent treatment is, in fact, this is maybe misleading, because when you do the consistent treatment, the improvement from, say, the search results to the High-Lumi results is really not quite so big. And so a consistent treatment is very important here for not getting misleading results. So to conclude, the question that I posed was, can this SMEFT be constrained correctly using standard model PDFs? Well, the answer is that if you're going to do that, then you really must take care, because if you inconsistently use PDF sets, then you can get artificially precise bounds, and you might expect something that really isn't really there. I want to point out that the ideal solution is really to do a simultaneous fit of Wilson coefficients and PDFs, because if you do something different and assume standard model PDFs, then there will always be this doubt in the back of your mind as to what the effect of this will be. And the best way to constrain the Wilson coefficients accurately is really to have the full sort of joint probability space of PDFs and Wilson coefficients, because you can't be sure that when you are doing your scans that you're near the global minimum of the chi-squared, for example, if you're just looking at the Wilson coefficient space and not ignoring the PDF space. So there's some non-negligible interplay between the two. So just to finalize, I wanted to talk about the next steps. So obviously it would be nice to generalize this, this procedure. So I just really looked at two models in this paper, and with only a couple of operators in each case. So it would be nice to consider some more general scenarios and also some other processes, so not just DIS and Drell-Yan. But to do this, I want to highlight that we want to build a more powerful methodology. So, we want to be able to build a methodology where we can simultaneously fit the PDFs and the Wilson coefficients and get accurate bounds for the Wilson coefficients. Okay, thank you very much for listening.
Thanks, Cameron. Very interesting prospects there for the future of FITs. So do we have any questions from the room?
Not at the moment.
Not at the moment. Okay, let's take one from here, from online, from Gauthier.
Hi, thank you for the talk. I'm not sure I understand precisely your comparison between standard model PDF and HEFT PDF. So, I mean, usually those tails of distribution are not included in standard PDF fits, right?
No, that's true. Typically, yes. But I think the reason is that typically you have large electroweak corrections, and those aren't included as standard in PDF fits.
Okay, so what is it that you do here? You actually use that data also in the standard model case you were showing. You're using the whole range of energies.
Yeah, exactly.
Okay. But if you were not to do that, would the impact be so big also? I mean, in the difference between the two fits?
So I think I know what you're saying, yes. I think the key point is that if you want to consistently do things as best you can, then you would want to include the data both consistently in your PDF set and also in your EFT analysis. So if you excluded the data entirely, yes, you're right that the bounds would then broaden slightly. But I think that I want to highlight that I think that is not the ideal thing to do. Does that make sense?
Yeah, I mean, it does, but I mean, if I just fit with, I don't know, I mean, the W and Y parameter, for instance, are very highly dominated by the very end of the tail. So if you just exclude those in a PDF fit and then fit a PDF and then use the last bins for the EFT, maybe that would be a more realistic comparison with respect to what we actually do now.
Sure, I know what you mean. But I think that this is not necessarily saying right now you should like be super concerned that everything is wrong, but rather that in the future this is something that must be thought about in more detail. And I think, of course, this is like a sort of a simple scenario in which you have one process and you have a rather simple model, but I think it's in the future more important to think about this when we have a lot more data and when we are doing more global fits. So I think that the impact is potentially more sort of relevant to actually looking for new physics.
Sure.
Future.
Got you. Thank you.
Maria, maybe you have a comment rather than a question. Perhaps it's a question as well. Go right ahead.
Thank you, Ken. No, I just wanted to point out that the data that Cameron presented in the high luminosity are the same that were studied for the projections for how to improve the PDF uncertainty for the high luminosity. So it's not that by default these things are not included in PDF fits. So the plan in the PDF words is to keep including more and more of this high tail data in the PDF fits, because in this way the large X uncertainty will be reduced, which is a problem for. So I think that, yeah, I just agree with Cameron, but just to say that these data are going to be included. So it's not, so perhaps PDF Fitter should provide some safe PDF data set, based on kind of safe data that are not contaminated by BSM effects. But that's a new message if you want.
Thanks, Maria. Yeah, that makes sense. Any further questions, either from the room or from the web? Maybe a quick one from me, final one. You mentioned that you use the search data as well. Is that independent from the high tail measurements? Do they use different events, or is it statistically the same dilepton events that are being analyzed?
It's a good question, actually, that I'm not too sure about, actually. Maria or Maeve, do you know the answer to that question?
I'm not actually sure about the statistical independence of them. I know it's completely different analysis. So these are like event level data presented in terms of number of events instead of a unfolded cross-section measurement. But Yeah, in terms of statistical independence, I'm not sure the answer.
Yeah, I think I'd have to do some digging and look at the exact data that went into each set. But it's a good point to think about.
Okay, thanks. Maybe we can follow up on Slack later on.
Yeah.
So good. Let's keep going. Still ahead of schedule. Looking very good. We can move on then to moving away from fits now and to more focused sensitivity optimizing strategies. And so we have Elena Venturini here. So if you would like to share your slides and tell us about the method of moments.